Hello everyone, and welcome back to this lecture series on BSP 303, that is Digital Systems and Application. So today is the fifth lecture of this Digital Systems and Application course. So in the last few lectures, we have seen various kind of number system, and we have also discussed how to convert one number system into another. Plus, we have also seen some binary arithmetic. So today we will start with the basic building block of all the type of digital circuits, that is the logic gate, and slowly we'll be moving further towards the Boolean algebra also. So let us start our discussion with the basic building block of digital circuits, that is the basic logic gates. So we will be discussing the basic logic gates first, and then we'll be moving forward towards the universal gate as well as the arithmetic logic gates. So let me share the screen and let us discuss first about the basic logic gates. Okay, so the topic of our discussion today would be, as you can see here, it is the logic gates. We'll start with the, the basic logic gates. So now let us first try and see what is this logic gates, which I have written the topic here. Okay? So now a logic gate, it is an electronic circuit which makes logic decision. So a logic gate will make logic decision. Let me write it here. A logic gate is an electronic circuit which makes logic decision. So it has one output. So it has one output, and we can say it has one or more inputs. And as I mentioned earlier also, so these logic gates are the building block of all the kind of digital circuits. Okay, they implement the logic function. This logic gate, they implement the logic function based on an algebra which is known as the Boolean algebra. Okay, so in computing systems, now if we consider the computing systems, in computing systems, so the number 0 and 1, they are used to represent two possible states. Okay, these binary 0 and 1 are used to represent two possible states. So those two possible states, they may be an on state or they may be an off state. Okay, we can represent the two possible states as on and off states. So sometimes they are also represented as closed or open states. Okay, and then similarly, they can also be represented as high and low states, and so on. Okay, so these two possible states in digital electronics, as I have already told you in the beginning of the lecture, that in digital electronics circuit are those circuit which used to process a discrete time signal. So the discrete time signal, something look like this, a clocked signal we can say. So it has only two possible values. Okay, so these, to represent these two possible values, so which may be either 0 volt or 5 volt, or depending upon what kind of voltages you are using. So the lower value is used to represent 0 and the upper one is used to represent 1. I'll be talking about the detail about this positive logic or negative logic. Anyway, they are used to represent two possible states, either 0 or 1, and they can be represented as on and off state, closed and open state, or high and low states, or true or false states. Okay, so suppose before I begin the logic gate, let me tell you one basic thing about the positive logic and the negative logic. Okay, so then we will go to, of course we will be dealing with a positive logic only in this course. So, but for clarification, let me tell you the difference between this positive logic, okay, and negative logic. So I'm just writing the negative logic here. All right. So now, what is positive logic? Now you know that this zero. Suppose we have a digital systems, and that digital system has two voltage level. So we have this 0 volt level and then 5 volt level. Okay. Now, if the lower voltage level is used to represent binary 0 and the upper voltage level is used to represent binary 1, then such kind of logic is known as positive logic. Okay. So here we decide that 1 is to represent plus 5 volt and 0 is to represent 0. So this kind of logic is known as positive logic. Okay. Now suppose I have two other voltages levels where I have minus 2 volt and let us say that I have 8 volt, minus 2 volt and minus 8 volt. So out of this, the lesser value is minus 8 volt and the higher value is minus 2 volt. So if the lesser value is assigned to 0, binary 0, and the upper value is assigned to binary 1, then it would be your positive logic. Whereas in the case of negative logic, it would be vice. It would be just the opposite. That means you will be using this lesser value to represent 1 and the higher value to represent 0. Then such kind of logic is known as the negative logic. Okay. So we'll be focusing on this positive logic representation in most of the cases in this course. So let us now move forward and try to see the first basic gate, that is we will start with the OR gate. Okay, let us discuss about this OR gate. So first I am going to draw the symbol for OR gate. The symbol may not be very much exact, so here we go. So this is a 2-input OR gate. I have the output Y and A and B are the 2 inputs. So in this OR gate, we see that we have 1 output and 2 inputs. Here A and B are the inputs and Y is the output. And let me write down the logic operation or the Boolean equation for this. So the Boolean equation would be Y equals to A or B. Now this is the OR operation. It is not similar to the normal addition operation. It is the OR operation. So the OR gate has an output of 1. Now based on this one, you can actually draw the truth table. And the OR gate has the output of 1 when either A or B or both are 1. If any one of the input is 1, then you will have a 1 high in the output. Or if both the input are high, then also you will have a high in the output. Okay. So I can draw the truth table here. I'm just writing in short as TT. Suppose I have the 2 input A and B, and then I have the output Y. Okay. Now first let me write down the possible combination of A, B. Those are 0, 0, 0, 1. Then I have 1, 0, and then finally I have 1, 1. Now when any of the input is 1, then the output is 1. In this case, the first case, both the input are low, so the output will be low. Here, one of the input is high, the output will be high. Here, one of the input is high, the output is high. Here, both the input are high, so the output will also be high. So this is the truth table, and here you can see the logic operation of a truth table. And this is the truth table for a 2-input OR gate. However, you may have another input as well. You can have 3-input OR gate as well. Okay, now let us go forward and see like what do we have here actually. I mean this portion. We are still unaware of this portion, isn't it? So we'll go and see that what is actually here inside, which is doing such kind of operations. Okay, so this OR gate, all these are constructed by using some diodes or transistors. Okay, so you can have either only a diode model, or you can have a transistor model, or sometimes you may also have a diode transistor model as well. Okay? So I will discuss two types of this OR gate model. That is, one is the diode model and another one is the transistor model. Okay, so let me go further and let me show you the diode OR gate first and tell you the working of that. Okay, we will be discussing the diode OR gate first. All right. I'm going to draw the circuit first. In this case, we have two diodes connected back to back in this way. Suppose I'm measuring the output across Y here, and the output is measured across this resistance. Let us call this resistance to be R. Okay. And here we have the two inputs. These are A and B. The inputs are given here. And let us say that the voltage, whatever is dropped here, it depends what is the voltage which you are giving. Suppose you are choosing the binary 0. Sorry, you are choosing binary 0 to be 0 volt level, and you are choosing binary 1, that is a high state, to be plus 5 volt level. Okay. Then you will have a drop of plus 5 volt here, neglecting whatever is the voltage drop across this, assuming that the two diodes are ideal. Okay, then you can have the same drop across the output. That means the output may be 0 volt, or the output may be plus 5 volt. 0 volt corresponds to 0, binary 0, and plus 5 volt corresponds to 1. All right. So now let us try to understand the working of this circuit. So I'm just choosing a different color here. Now I will represent the one diode as the diode D1, okay, and the other one as the diode D2. Now, what happens when I apply the input as, when A is when I apply the input as 0, 0, what happens here? 0, 0 means I'm applying 0 volt here and I'm applying 0 volt to B. Now you see this is the P side of the diode and this is the N side. Now if you are giving 0 volt to the P side of the diode, then it is reverse biased. Okay, you can say that the diode is reverse biased. That means plus okay, when these are 0, 0, these two diodes are, they are reverse bias, and there is no question of, the output will also be 0 volt. Okay, since no current can flow through this diode D1 and D2, and there will be no drop across this resistance R. So you will get the output also to be a 0, that is 0 volt. All right, let us see another case. Now let us see the case when any one of the input is any one of the input is high. So let me apply plus 5 volt here and 0 volt here. That means I'm giving a binary 1, as if I'm giving a binary 1 here and 0. Now you see that the input A, I'm applying plus 5 volt. That means this plus 5 volt will forward bias this diode. Okay, then what happens? Current will start flowing through this diode, and then it will be flowing through this resistance to the ground. That means whatever voltage you are applying, all this voltage will be dropped across this resistance R. And what is output? Output means nothing but you are measuring the voltage across this resistance. Whatever is the voltage across this resistance, that is your output voltage. That means the current is flowing. So that means that the voltage is dropped across R, and then you will get a plus 5 volt at the output. Again, I am saying that neglecting whatever is the drop across here. If it is a silicon diode, the drop across this diode would be 0.7 volt. In this particular case, we are neglecting it. So whatever voltage you are applying here, that is dropped because the diode is now working. Okay. Similarly, if you reverse the situation, the same happens. If you reverse the situation, for example, let us go back. And let us say that you are giving a 0 here, and then you are giving a 1 here. That means 1 means plus 5 volt, that diode D2 will work, and then the current will start flowing. Again, the current will flow through this to the ground. Okay, then there will be a voltage drop. So you will get a 1 at the output. So you will get a high in the output when any one of the input is high or when both are high. Now, when both are high, also same things happens. Current will start flowing through this also. Then you will have the same drop. And you know that when these are connected in parallel, so it doesn't really affect. You will have only 5 volt at the output here across R. That means Y will be equal to 1. So when in this way, when any one of the input is 1, or when both are 1, you will get a high output. Otherwise, you will get a low output. So this is a very simple diode model of OR gate. In this way, you can even in your laboratory also, if you have some breadboard and then if you have some basic diodes and some 5 volt battery, then you can easily demonstrate the working of a logic OR gate. Okay, fine. So similarly, we can also build a transistor model. I mean, with the help of transistor, we can build the OR gate. So let me just go and write down here. So now we are going to see the transistor OR gate. Okay, so transistor OR gate. Let us discuss this first. So we require 3 transistors to do so. I'm writing one transistor here, another one somewhere here, and the other one somewhere. Okay. So there are 3 transistors. So all these are NPN transistor, as this arrow indicate. These are NPN transistor. Suppose I have the second transistor here. My diagram may not be very perfect, but I hope it is clear to all of you. So now you know the working of a transistor. Okay, if you do not know, then I will explain you the working here first. So these are the transistors. Now let me tell you about the transistor. Suppose this is my NPN transistor. Suppose this is the NPN transistor. Now see, you know that this is the base of the transistor, and this is the collector of the transistor, and this is the emitter of the transistor, because this arrow indicates that this side is the emitter side, and the outward arrow indicates that this is an NPN transistor. So this is an NPN. That means collector is N, base is P, and emitter is N. Now, on what condition the current can flow through the diode? Let us try to imagine that situation. I'm just going to rub this off. On what situation the current will flow through the diode? Suppose you applied the basic condition is that the base emitter junction should always be forward bias, and the collector emitter junction should be reverse bias. Okay. So that means, see, the current can flow through this collector to emitter. The current can flow through the collector to emitter only when you trigger the base with a very small positive voltage, because this is an NPN transistor. The base is made up of P. Even though you forward bias these 2 sections, okay, now suppose you have applied some voltage across the collector and the emitter, but still current cannot flow until and unless you trigger the base with a positive voltage. The reverse will happen for an PNP transistor. You need to trigger the base with negative voltage. However, in this particular case, we are considering an NPN transistor. So therefore, the current can flow from the collector to the emitter only when you trigger the base with a positive voltage. So let us just remember this one, and on the basis of this one, we'll try to understand the diode, the transistor OR gate. Now let me go forward and complete this figure first. So here we are going to connect one resistance, okay, and then similarly on this another side also we are going to connect this resistance. Now what I'm going to do, I'm going to connect these things to some voltage, let us say plus 5 volt. Okay, I'm going to connect this to some voltage plus 5 volt, and then okay, let me connect this here. This is one connection. And then the output the output of the second transistor will go as the input to the next one. Okay. And this one, the base of this we will take as the input B, and the base of this one will take as the input A. Okay, so all right, so here we go. Fine. So now these are our two inputs A and B, and we'll obtain the output across this terminal. Okay, now I will call this point as N and I will call this point as M. Okay, and whatever is the voltage at M, that will be the same voltage as Y, the output Y. Okay, now let me name this transistor as Q1 and the other transistor as Q2 and this one as Q3. Now the output will be high only when I mean either when A or B or when both are high, then only the output will be high. Now let us first see the low case. Okay, now let us say when this is 0 and when this is also 0. Now you know that when you apply a 0 volt to the base of this NPN transistor, then the transistor Q1 will not work. That means no current can flow through this Q1. Similarly, the transistor Q2 will also not work. Okay, similarly, the transistor Q2 is also not work. Now what happens? Whatever is the voltage here, this in this case, the point N will be driven to a positive potential actually. Nothing will be dropped here because the circuit is not complete. If the current flows through this one to the ground, then the voltage would be dropped here. But in this case, since the current cannot flow through these two transistors, like the current cannot flow through this part to the ground, similarly the current cannot flow through this transistor to the ground, then what happens? In this case, the transistor Q1 and Q2 will not work, and then whatever is the potential applied, that potential will appear across N. That means the point N is at a positive potential. Now this point N is connected to the as the input to the transistor Q3. That means this positive potential will drive this transistor into active mode. Okay, and then this transistor will go start working. The transistor Q3 will start work. Then what is the meaning of that one? Like if the transistor Q3 will work, the current will flow. The current will flow like this to the ground. Okay, and whatever is the voltage here +5, it will be dropped across this resistance R2. Let me call this resistance as R2 and this one as R1. So in this case, all the voltage will be dropped across R2, and then the point M will go to zero potential. The point M will go to 0 volt because the current flows through this resistance R2 through this transistor to the ground. All the voltage will be dropped across R2 and nothing will remain on M. That means M will be at a zero potential. Now, if M is at zero potential, therefore Y will also be 0. Okay, so this is the condition when both the input are 0, the output is also 0. Now let us go and see the other condition. When any one of the transistor is working, what will be the case now? Okay, when any one or when both are working, this will be similar when either any one or both are working. So let us say that the transistor, I'm giving a 0 here and 1. That means I'm giving some positive potential to the base of this transistor Q1. The transistor Q1 will work and the transistor Q2 will not work. Let us forget about this Q2. Q1 will work. The transistor Q1 will work means what happened now? The current will flow through this, okay, and through this transistor from the collector of the transistor emitter to the ground like this. Okay, in this condition, what happens? Whatever is the voltage appearing here, it will be all dropped across this resistance, this particular resistance, and as a result of which the point N will go to zero potential, because in this case, remember, the current is flowing. That means all the voltage will be dropped across this particular resistance. That means the point N will not have a positive potential, rather it will have a zero potential. Okay, that means now since the point N will have a zero potential, that means which is connected to the base of Q3, the transistor Q3 will not work. In such a case, what happens? Whatever is the voltage across this one, current will not flow through this transistor and the voltage cannot drop across this resistance. That means whatever is the voltage, it will directly appear across M. That is, the point M will be plus 5 volt. That means it is 1, or the output will be plus 5 volt. Okay. So in this way, I mean, this condition is valid for when both the transistors are working also. Suppose if you apply 1 here, okay. So let me just erase this. If you apply a 1 here also you suppose you have applied a 1. Both the transistor will work, and then the current will flow through any one of the transistor. In such a situation also, the point N will be driven to ground potential. That means 0 volt. Okay, and hence the transistor Q3 will not work. So when either of the input, or when both the input are 1, any one of them is 1, these transistor will not work. The other two will work. Any one of them or the two will work, and the transistor Q3 will not work. So whenever this situation arrives, when the transistor Q3 is not working, whatever is the potential, it will all appear across the output. That means the output will be high. Okay. So in this way, I mean, you can build a diode OR gate or a transistor OR gate. This can also be easily I mean, constructed and demonstrated in your laboratory. If you have a plus 5 voltage battery and then some resistances, some transistors, and a breadboard, then you can easily see the logic implementation of this gate in your normal laboratory. Okay, fine. So this is the so in a similar way, you can also have a 3-input. I mean, you can also have a 3-input OR gate. Okay, and now let me. All right, fine. So an arithmetic gate can be also done. We can use an arithmetic gate, which is known as an exclusive OR gate. Okay, we'll see that. I mean, it would be wise to see when we will discuss separately, like what are the universal gate, and then after that this NAND gate and NOR gate, and then after that again we will discuss the arithmetic gate. But for now, I think we'll discuss with this OR gate only. Now, next in the next class, we will try to see the other two gates. I mean, that is the AND gate and the NOT gate. Then we will go to the then we will go to the universal gate and some Boolean algebra. I mean, the Boolean algebra, and then we will try to see the arithmetic gate as well. Okay, so for today, okay, let us stop here. So I hope today's lecture is clear to you all. So I am stop sharing the screen now. And then, okay, so we have come to the end of today's lecture. So thank you everyone for joining the lecture. So in the next upcoming lecture, we will discuss some more logic gates, and then we'll go to the Boolean algebra. So thank you very much, and then see you all in the next lecture. Thank you.